Now, parallel operation of transformers. In order to meet the load in excess of the rating of the existing transformer, a transformer or more transformers are added in parallel with the existing transformer, and which is called as parallel operation of transformers. This is the existing transformer whose primary windings are connected across the supply bus bars and secondary windings are connected across the load bus bars, and here the transformer is taking power from the supply bus bars and delivering that power to the load through load bus bars. If suppose load is of 30 kVA and the transformer rating is of 50 kVA, here transformer can supply the required power to the load without overheating, because the load requirement is less than the transformer rating. If suppose the load kVA is now 130, and now as the transformer rating is less than the load requirement, here the transformer can't supply the required power, and if it is left like this, then this transformer will get overheated. Therefore, to supply the required power to the load, here what we must do? We must add a transformer in parallel with the existing transformer such that the both transformers will supply to this load. So let us suppose this is the additional transformer which we are connecting to the existing transformer in parallel with it. So the primary windings are connected in parallel with the existing transformer like this. Now this represents two transformers operating in parallel, and now if the transformer rating is now, let us suppose 100 kVA, now these two transformers together can supply the required power to the load. But here the most important point that you must keep in mind in case of parallel operation of transformers is that here the transformer terminals of same polarity are to be connected to the same polarity bus bars. That is, phase terminal of transformer 1 and phase terminal of transformer 2 are to be connected to the phase bus bars, and neutral terminal of transformer 1 and neutral terminal of transformer 2 are to be connected to the neutral bus bar. If this is not done, that will lead to a dead short circuit. So here are the essential conditions that to be followed for safe and proper operation of transformers. The first essential condition is primary windings of transformers must be suitable with supply voltage and frequency. And the second essential condition is transformer terminals of same polarity must be connected to same polarity bus bars. And the third important condition is transformers must have same X/R ratio. That is, we know that power factor angle phi is equal to tan inverse of X/R, which implies that here if transformers having different X/R ratio, then it will indicate that transformers will operate at different power factors. That is, if the transformers are operating at different power factors, which will lead to unequal load sharing by the transformers. Therefore, for proper parallel operation of transformers, the transformers must have same X/R ratio. And the fourth condition is transformers rating must be inversely proportional to their respective impedances. That is, S is inversely proportional to Z. Let us suppose transformer 1 is having a rating of SA and transformer B of rating SB. So SA by SB is equal to ZB by ZA. SA can be taken as equal to the terminal voltage into load current, and here the terminal voltages are same because these two are operating in parallel. So let's take that common voltage as V. Now let's rearrange this equation. So which implies IA into ZA by V, and which is equal to IB into ZB by and if you multiply 100 on both sides, that will give you percentage impedance drop, and which is simply can be termed as percentage impedance. So which implies percentage impedance of ZA is equal to percentage impedance of ZB, or you can represent like ZA by V by IA. So V by IA is impedance, and this will represent the per unit impedance. So you can write per unit impedance of transformer A is equal to per unit impedance of transformer B. So the fourth condition can be termed as either the transformer rating must be inversely proportional to their impedances, or their percentage must be equal, or their per unit impedance must be equal. And the fifth important condition is transformers must have same turns ratio, which is also called as same transformation ratio constant K, which will indicate that the transformer induced EMFs must be same. If the transformer induced EMFs are not same, then in this circuit circulating current IC will flow, and because of which transformer will share the load unequally if circulating current flows. And of these conditions, first two conditions are very essential. If these two conditions are not met, then parallel operation of transformer will not happen. Whereas even these three conditions are not met, parallel operation is still possible, but there will be unequal load sharing. That is, there will be inappropriate load sharing. That is, if suppose transformer 1 is having 10, and let us suppose transformer 2 is having 20, and let the load be 30. So if all these conditions are satisfied, then this transformer has to share one part, and this transformer has to share two parts. This is proportionate sharing. If suppose of these 3, 4 and 5th conditions, any condition is not satisfied, then there will be inappropriate load sharing. Let us suppose this transformer is sharing 1. This transformer might share less than 2. Let us suppose 1.5 part. So which is inappropriate load sharing. And here this transformer is supplying less than what it is expected to supply. Then what happens? The burden on this transformer will get increased, and this transformer will get overheated. Therefore, for proper parallel operation of transformers, these conditions are to be satisfied. And here are the advantages of parallel operation of transformer. The most important point here is reliability, because in parallel operation of transformers, if suppose a single transformer is supplying power to the load, and due to some unknown reason, if this transformer gets failed, then what will happen? This load will no longer receive the supply, and which will indicate that here this load is having discontinuity of supply. In power systems, one of the important criteria that to be maintained is continuity of supply. How good the quality of power supply may be. If there is no continuous supply, what's the use? Therefore, in power systems, with the quality, the continuous supply is also one of the important criteria that to be maintained. And coming to the parallel operation of transformer, if these two transformers are supplying power to the load, due to some unknown reason, if one of the transformer gets failed, then continuous supply can be maintained through the other transformer. So here the important criteria, that is continuous supply, can be maintained in case of parallel operation of transformers. So is why reliability is more. And the second advantage is future load demand can be met. And in parallel operation of transformer, one of the transformer can be used as standby. That is, for supplying power to the load, even there is no requirement of two transformers, one transformer is used as standby for safety purpose, because if one transformer gets failed, then continuous supply can be maintained through the other transformer. So in parallel operation of transformer, one of the transformer can be used as standby. Here in parallel operation of transformers, there are two important points that must be discussed. That is, in parallel operation of transformers, if transformers are having same rating, then to share the load in equal proportion, their impedances must be same. And here you must keep in mind that Z is not numerical value. Here, if transformers are of same rating, then to share the load equally, their impedances must be same, means all the transformers resistance and reactances must be same. And the second point is, if transformers are of different ratings which are in parallel operation, then their ratings must be inversely proportional to their respective impedances. And here impedance is numerical value. That is, to share the load in equal proportion, high rating transformer must have low impedance. And you must understand this big difference between the numerical value and impedance. Here it is not numerical equality, and here it is numerical equality. And here there are three cases that we must study, that is transformers having same turns ratio and same X by R ratio. Here the same X by R ratio means the transformers having same impedance triangles, that is impedance triangles of same shape and size. And the same turns ratio means the secondary induced EMFs are same. And the schematic diagram of two transformers which are operating in parallel can be drawn like this. This together represents the primary winding of both transformers, and this represents the schematic diagram of two transformers operating in parallel, and this winding represents the primary winding of both transformers, and these two represents the secondary winding of transformer A and transformer B, and this is the impedance of transformer A and this is the impedance of transformer B, and the current flowing through transformer AB IA, and the current flowing through secondary winding of transformer BB IB, and these two together are supplying a current of I2, and V2 is the terminal voltage, that is load voltage. Now let's write the important equations from this, and I2 is the vector sum of IA and IB, and as here transformers having same turns ratio means secondary induced EMFs are same, so EA is equal to EB, and also IA ZA is equal to IA ZB, and you can write the voltage equation EA is equal to this drop plus this, that is it is vector sum of IA ZA and V2, and EB is equal to IB ZB plus V2, that is vector sum of IB ZB and V2. And now let's draw the vector diagram. If suppose this is the terminal voltage V2, and let us suppose the load be lagging by an angle phi 2, and let the load current be I2, and now to get E2, that is to get EA, we must add vectorly IA ZA to the V2, and as the transformers are having same X by R ratio means they are having same impedance triangles, which implies that the currents in transformer 1 and transformer B will be in phase, means IA and IB will be in phase with I2, and now to get EA we must add IA ZA to the V2, so IA ZA means IA RA drop and IA XA drop, so IA RA drop will be parallel to the IA phasor, so from V2 let's draw IA RA, and now we must add IA XA drop which will be perpendicular to the IA phasor, so from here maintaining perpendicular with IA, draw IA XA drop, and now the resultant of IA RA and IA XA is IA ZA, and now the resultant is EA, and similarly we must get EB. So to get EB we must add IB ZB to the V2. So from V2 we must draw IB RA drop and IB XB drop, and then we will get EB. So as here the transformers are having same XY ratio, that is their impedance triangles are same, which means we need not draw the transformer B impedance triangle, because the transformer B triangle will look like superimposed on the transformer A impedance triangle. Therefore simply you can represent now like this: EA is equal to EB. And here the important equations in this case is current IA is equal to I into ZB by ZA plus ZB, and current IB is equal to I into ZA by ZA plus ZB. Here I is the load current I2. And now coming to second case, same turns ratio and different X by R ratio. So different X by R ratio means the impedance triangles of both transformers are different. That is, now in phasor diagram the impedance triangles will not superimpose on each other, they will look separately, but as same turns ratio, so EA and EB will be remain same. So now let's draw the transformer B impedance triangle, and as the impedance triangles are different, which will imply that the currents of transformer A and B will not be in phase. So let IA be like this and IB be like this, and we must draw IRA drop parallel to the IA phasor. Please keep in mind that IRA drop must be parallel with IA phasor. And now let's draw the transformer B impedance triangle. So from V2, maintaining parallel with IB, draw IB RB drop, and then maintaining perpendicular with IB phasor, draw IB XB drop, and now the resultant is EB. And EA and EB are on same line because same turns ratio. The only difference here in this phasor diagram when compared with previous diagram is different impedance triangles and out of phase currents IA and IB. And the important equations corresponding to this case are SA is equal to SC into ZB by ZA plus ZB. Here SA SB represents the part of load shared by transformer A and part of load shared by transformer B. S is the load rating, that is V2 into I2. Now case 3, different turns ratio and different X by R ratio, means here the transformers under parallel operation are having different turns ratio, means their induced EMFs are not same, and different X by R ratio means their impedance triangles are also different. And now coming to the phasor diagram, here the difference between this and the second case is that EA is not equal to EB, means now EA and EB phasor will not look like superimposed, they will be different. That is, let's draw like this: if this is V2 and if this is the load current I2, and let the transformer A current be IA and transformer B current be IB. So to get EA we must add IA ZA drop to V2. So IA ZA drop means IA RA drop plus IA XA drop. So IA RA drop will be parallel to IA phasor and IA XA drop, which is perpendicular to IA phasor, and the resultant is EA. The resultant of IA RA drop and IA XA drop is IA ZA drop. Now let's draw the transformer B impedance triangle. So IB RA drop will be parallel to IB phasor, and IB XB drop is perpendicular to IB phasor, and the resultant of IB RB and IB XB is IB ZB drop. Now the resultant of V2 and IBZB is EB. So if you compare this phasor diagram with this, the only difference is EA and EB are different. This is second case in which EA and EB appear like superimposed on each other. And the important equations under this case are IA is equal to and IB is equal to, and you can find I2 by the vector sum of IA and IB. And here V2 can be found by applying Millman's theorem. So if you look at this circuit, it will look like a voltage source in series with impedance ZA and a second voltage source in series with an impedance ZB, and this is load impedance ZL and in series with a voltage source of 0V, and this is V2. Now this circuit will look like the voltage sources with their internal impedances connected in parallel. So we can find voltage V2 by applying Millman's theorem. So V2 is equal to EA by ZA plus EB by ZB plus 0 by ZL whole divided by 1 by ZA plus 1 by ZB plus 1 by ZL. These are the important equations corresponding to this case 3. Now, before ending the discussion on parallel operation transformers, it is very essential to discuss an important concept that will make us to solve the numerical problem. So this is the numerical example in which here there are two transformers which are operating in parallel, and they have to share a load of 125 kVA at 0.8 power factor lagging, and these are the corresponding values of transformer A and transformer B, and here we need to find the load shared by each transformer. So this is the load, and we need to find the load shared by the transformer A and load shared by the transformer B. We have SA is equal to S into ZB by ZA plus ZB, and SB is equal to S into ZA by ZA plus ZB. And observe that here for 100 kVA these are the corresponding percentage resistance and percentage reactance, and for 50 kVA this is the percentage resistance and this is the percentage reactance. Means these resistance and reactance values are corresponding to different ratings. And here what we must do for solving this numerical problem is that we must adjust these values to the same rating. That is, keep 100 kVA as it is, and let's adjust the 50 kVA to 100 kVA. Means 50 kVA becomes 100 kVA by multiplying with 2. So by adjusting to same rating, resistance value changes to 2.0 percentage and reactance changes to 2 into 5, means 10 percentage reactance. So now we must use these values here to find the load shared by each transformer. This is RB and this is XB, and this is RA and this is XA, and S is 125 kVA. And now by substituting all these values and solving, we will get SA is equal to 63 at an angle minus 40 degrees, and SB is equal to 62.1 at an angle minus 33.8 degrees. So of 125 kVA, transformer A supplied this power, and of 125 kVA, transformer B supplied this amount of power. Means these are the loads shared by transformer A and transformer B of 125 kVA. Thank you for watching. If you like this video, please like this video, share this video, and do subscribe to this channel. Thank you. See you in next lecture.